welcome to the module. We have not completely finished our signal conditioning circuit. So, for that we have to change our mapping factor. How do we do that? So, right now we understood that for 1 volt I am getting 10.215 and for 5 volt I am getting 0.2 volt, but I need for 1 volt the output from the integrator should also be 1 volt, whereas for 5 volts the output should also be 5 volt. That means 10.215 has to be converted to 1 volt and 0.2 volt has to be converted to 5 volt. How do we do that? And everything should be of linearly, which means that when this is linearly varying, the output should also linearly vary. That means when the input is 7.9 I should get output as 2, when the input is 7.9 I should get an output of 2. Then the input voltage that is giving at the set point is equal to the output voltage from the signal conditioning circuit. Both are having the same mapping factor, but how do we do that? So, for that we have to further design a signal conditioning circuit. So, what we do? So, we know x1 what is the input that we are giving and we know what is an output that we need to get it. That means, when I put a scale, right now the scale is like this, I want to change the scale from there to this. This is the input scale and I want to get it as an output scale, right. So, one way, if I want to graphically understand it, what I can do, if I invert this particular input signal, so what do I get if I invert the signal? So, if I invert the input signal, wherever the negative I have, I will get a positive. So, one good part is that I got, in this case the input is negative slope, now it has been changed to a positive slope, right. Slope is keep on increasing. Then whatever the offset that I have, if I remove it, remove offset or add some offset to the system, so that it will go to this part, right. So, but graphically it is easy for us to understand that I have to do the inversion and then I have to provide an offset, so that this particular signal will shift from 0, but what values, what magnitude of offset that I have to provide and what magnitude of slope that I have to do give such that the input that we provide to the system will get an output of this one. So, we require a theoretical understanding of conversion of this signal. If you apply some mathematics into that, we know that input in this case is 10.215, output we require is 1 volt, whereas when the input of 0.2 I require an output of 5.2. So, I will apply equation of line formula, which says that y minus y1 is equal to y2 minus y1 by x2 minus x1 into x minus x1. So, what is y minus y1? Y minus 1 volt is nothing but, sorry, y1 I am considering 1 volt, 5 minus 1 divided by 0.2 minus 10.215 into x minus x1, x1 is 10.215. So, when I do this calculation, 4 divided by 10.215 minus 0.2, which I got minus 10.015, right. Then 4 divided by 10.015, when I do, I got 0.4. This value is approximately of 0.4 because 0.399. So, I will change this to 0.4, 0.4 into x minus 10.215, which means that y. So, let me write down here. So, y is equal to minus 0.4 plus 0.4 into 10.215, which is 4 plus 1. That means if I provide a slope of 0.4 magnitude, that too the negative slope with an offset of 5 volts, then my problem would be solved. So, which means that so first case when I provide a negative with a slope, which means that I will get this particular signal, this particular slope, which is a positive slope, because initially we have a negative slope, we have to change it to positive slope. Then I have to shift it little bit. So, for shifting we are using offset, which is 5 volts. So, when I provide a 5 volt signal to the input to this, it will go to 0 to 1. So, why do not we apply some formula? So, minus 0.4 into 10 when we do, it will be somewhere around 4 minus 4 plus 5, which is 1 volt. So, we are getting it. So, 7.98. So, 0.4 into 7.9, which is 3.16 plus 5, approximately of minus 1.84, which is 2 volts, into 0.2 which is 4.92, approximately of 5 volts. Let us see for 4 volts too, 0.4 into 2.7 minus 5. So, we are getting 3.92, which is 4. So, for all set of values we noted that this is working fine, but how do I implement this? How can I get a signal conditioning circuit with a slope of 0.5 with an offset of 5 and that too negative slope? So, if you recall, at this particular point what we are doing? We are doing a multiplication. The input has to be multiplied with a factor of 0.4, then whatever the output that we get has to be subtracted with 5 volts. Why do not we simply use a inverting amplifier in this case, which gets a negative output, then add with 5, inverting amplifier plus adder? Yes, of course we can use that too, because op amps are generally meant for doing so many operations like multiplication, addition, division, everything, right. So, we can also do that, or if you remember the difference amplifier, with a single operational amplifier we can do the difference between the two signals. So, if I implement a difference amplifier with a gain of 0.4 and 0.4 and the input as 5. So, if you recall our difference amplifier, say this is V1, this is V2, R1, R2, R1, R2. The output voltage, we know that output is nothing but R1 by R2 into V2 minus V1, right. But in this case, if I make R1 RF as a constant, then the parameter will completely change. So, because of that I do not make R1, this R1 and this one R1 as same. So, I will take a different R1s R2s. So, which means that if I recall, say if this is my this particular value V2. So, we know that V0, applying superposition principle, I can write it down as V0 is equal to minus R1 by R2 into V1 plus 1 plus R1 by R2 into V2 is output. So, when I correlate with respect to this and this, right. So, this particular value I should get it as 5 volts, this particular should be minus 0.4, whereas V1 is nothing but input. So, if I connect input X here, if I connect the complete with 5 volts, which means that the set of 1 plus R1 by R2 into V2 should be 5 volts. That means what input voltage if I connect at this point, I will get 5 volts. So, in order to get that value, so first we will come out with R1 and R2 values, then we will see R3 and R4, which to provide for this, right. So, we know that R1 and R2 we require to be a 0.4. So, if I take R2 as 10 kilo, in this case we have taken somewhere around 8.2 K. So, R1 is equal to 0.4 into 8.2 K. When I do the calculation, 0.4 into 8.2. So, we got somewhere around 3.28 K, right. So, since we do not get a 3.28 K commercially or in market, what we have used is that we used a pot of 10 kilo ohms resistance. So, by varying the pot we can change the gain at this point. So, this problem is solved. So, we have considered R2 which is nothing but R4 in my case is 8.2 kilo ohms. Then R6 is a pot we have considering on behalf of our R1 to set the gain to get the required output. So, that we can tune the gain as well as an offset in order to properly match 1 volt with 1 volt, right. So, this part is done, but what about this part, right. So, in this case R1 and R2 are fixed right now for us. So, R1 and R2 should be 0.4. So, that means 1 plus 0.4 into V2 should be 5 volts. So, that means that V2 should be 5 divided by 1.4. So, 5 divided by 1.4, which means that 3.57. So, if I can provide a 3.57 volt at V2 point, right, we can get output voltage of V naught. So, that means when the input is 1 volt, we also get output as 1 volt, provided the input should be connected to the motor at the set point, at the encoder to the motor, right. So, but getting 3.57 exactly will be very difficult, and these are the ideal values. Practically there will be a slight offset and the gains as there will be a slight variation in the offset as well as gain that we set here, right. So, in order to make it realistic, what we have considered is that we have considered the input voltage as 15, because all the op amps are powered with 15, it is very easy to take it. Otherwise, again we have to take another voltage source which should properly match with that, and instead of providing directly 3.57, the 15 is connected to a potential divider circuit. So, something like this. This is 15 volts we are doing. So, this complete set this R, so in this case R5, R5A, R5B. The addition of R5A and R5B is nothing but 10 kilo ohms, and since it is a pot we are considering at this point. So, by properly changing the position of our wiper, we can get output voltage of 3.57. If I can achieve the 3.57 and connect it at this point at the positive terminal of our operational amplifier, then our problem is solved. So, this is what we are doing it here. So, why do not we try it? So, we will open Multisim now. So, what I will do is that I will create a circuit in a new file. So, I will take op amp, let me flip it, then I will take a potentiometer. So, as we have already seen, the offset is providing by using this potentiometer. I will connect the wiper of the potentiometer to this terminal, and the supply that we are using is 15 volts. So, I will take a voltage source of 15, connect it at this point, whereas the other terminal should be always grounded, right. Then the input voltage we have designed it for 8.2 K, right. Then this particular input voltage, which right now we assume it as this input voltage, we are getting it from the output of integrator, right. So, which will be varied from 10 point something to the value. Then the feedback resistance is also another potentiometer. The purpose of this we are using a potentiometer because any variation we can easily if I want to change the gain, we can easily change it if I have a potentiometer, right. Now circuit is ready, but only thing is that we have to take a values 8.2, 10K and another 10K. So 10K and 10K. Now let me check what is the output voltage we are getting at this point. So what I will do is that I will connect one probe here, I will connect one more probe here. So for time being, now I am applying input voltage. So we need this to be 3.7. This should be 15, that is another problem. Of course, we can also provide with 12 volts too. Let me try for once again. We need 3.57. So I will change it to 3.6. Okay. So for 10.215, I should get somewhere around 1 volt, approximately 93. So let me change this value. Yeah. So we got 1 volt. Then the second set should be somewhere around, the value is 7.9. So I will change it to 7.9. We should get 2 volts. Let me try. Yeah, we are getting 1.911, almost close to 2. Then I will go with another set which is 2.7 volts. I should get somewhere around 4. We are getting 3.95, which is also close enough. Then other value is 200 milli, we should get 5. So which are also coming very close to 5 volts. But there will be always a difference between your theoretical and ideal again, right. So because of that reason, we have given the feedback resistance as well as this resistance, instead of giving a direct resistance, we have taken it as variable resistor, so that in order to properly tune your output signal. But no matter what, if we follow this particular the idea, we can easily convert our linear the negative slope signal into a positive slope signal with a simple single operational amplifier, right. Now we understood that with input voltage of 10.25, after passing through the signal conditioning circuit that we have designed, we are getting 1 volt, whereas for 2 volts we are getting 1.9 volt, somewhere around 2.7 we got 3.9, and whereas for 5 volts we got 4.93, right. So which is very close, but we have not tried for that, but okay. So now from this it is clear that whatever we apply, whatever we require from the signal conditioning circuit are almost same, right. So that means that when we look into our closed loop control system, now we made the sensor signal conditioning output, that means the sensor plus signal conditioning output, which is nothing but a feedback signal, is having the same mapping factor as input. Now our problem is solved, all the block systems are done, we have looked into the error detector, we have also looked into driver circuit for the DC motor, which to make run even from the output from controller by using operational amplifier as well as transistor. Then we have also seen the characteristics of our motor, right, and we have also seen the characteristics of our DC encoder. Since the encoder signal is providing me the digital pulses, we require an linearly output varying signal based upon the change in the RPM of motor with respect to the change in the input voltage to the motor. We also understood that in order to do that, we have to design a signal conditioning circuit, and we have done first part of a signal conditioning circuit to make it a linearly output by using integrator as well as monostable multivibrator, but the slopes are not matching with respect to the input slope. Then we have also designed the second set of signal conditioning circuit to the sensor, so that now the output of the complete circuit is mapping with respect to the input. In the next module we will see interfacing the output of a DC motor to sensor signal conditioning circuit and we will see whether we are getting the same linearly varying output signal or not. Then after that we will design a controller, we will discuss about the controller, then we will see we will understand about the controller parameters. Once we complete our explanation about that, we will interface each and everything, then we will discuss about it. Till then, take care.